The first paper in this session is tabulating Carmichael numbers n equals PQR with P small, and Andrew Shallue will be presenting.
Thank you. Thank you to the organizers. Thanks everybody for being here on an early Friday morning, although thankfully not quite as early as other days. And I especially want to thank the reviewers, many helpful comments, which we definitely plan to integrate into the final version of the paper. One, I bring this up because one of the comments by the reviewers was a very reasonable question: why Carmichael numbers with P small? And so the short background of where this project came from is that originally Jonathan and I were interested in applying Richards-Pinch's tabulation algorithm to higher order Carmichael numbers. Higher order Carmichael numbers are something we've been studying from a couple of different angles. And Jonathan discovered, oh, hey, I think we can improve Pinch's algorithm in one case, the case where the pre-product is small. And so that's where this paper came from. I'll talk a bit more later about how we think that this is going to lead to a better overall tabulation algorithm, but we can't make any specific claims about that yet. That's for future work. So that's the overview. Here is, so here's the overview of the talk: definitions, problem motivation, previous work, and new work. So the overall setting for this talk is primality testing and pseudoprimes. We now have deterministic polynomial time algorithms for primality, but in practice, people still are tending to use probabilistic algorithms because they are faster. Probabilistic algorithms have the advantage of giving you an answer very rapidly and having an extraordinarily small chance of error, but the disadvantage is that there are composite numbers that pass this test, and we call these pseudoprimes. In this case, we have Fermat's theorem: if P is prime, then we have this congruence. So we get what one might call a compositeness test. One thing I've encountered is people saying, rather than calling them primality tests, we should call them compositeness tests, because really that's what we're doing. We're checking for compositeness. And if we don't find it, then we throw up our hands and say, maybe it's prime. So the contrapositive gives us a compositeness test, and then a Carmichael number is a composite integer n that satisfies this congruence for any a. And it's important to note that there are infinitely many of these numbers, as proven by Alford Granville Pomerantz. Now, that definition of Carmichael numbers shows the interest in it. It's a pseudo-prime that's maximally bad in some sense with respect to the Fermat test. But in terms of working with Carmichael numbers, Korselt's criterion tends to be more useful. So what we have here is that it's a Carmichael number if and only if it's square free, and we have this divisibility condition for all prime factors P of n. For me, so there's the application to primality testing, but for me, what really attracts me to pseudoprimes is this divisibility condition. This is the divisibility condition for Carmichael numbers, but you have different divisibility conditions depending upon the pseudoprime that you're looking at. There's a great diversity of different pseudoprimes with different divisibility conditions. And for number theorists, I think this is very interesting to study just on its own as well. So this is the definition that we're going to be working with. Here's the smallest example, 561, smallest Carmichael number. And then OEIS can tell us the first several Carmichael numbers. So here are the first several. Now, a long-standing debate about Carmichael numbers is getting a sense of how many there are. I'm going to talk about this more in a second, but just looking at this list, one might think these are kind of rare. You know, I don't know, it depends upon our yardstick, I guess. More rare than the primes, but more common than some other numbers perhaps. But it's sort of a natural question of thinking about how many of these are. And so that leads to an algorithm for tabulating them to get some sense for how often these numbers appear. So the particular problem that we are focused on here is the one up at top: given bound B, tabulate all Carmichael numbers up to B. That's the overall problem that is motivating us. We, my co-author and I, were able to make progress on the second problem. So we are mostly providing a result, a new result for the second problem. Given an integer, capital P, called a pre-product, determine the finite list of pairs Q and R so that then you end up with PQR being Carmichael. The fact that this is a finite list was proven by Richard Pinch in his original paper on this. And so then that becomes the natural question, is to figure out the completions for a given pre-product. And then what you can do is you can turn this into an overall tabulation algorithm by breaking into two cases, either a small pre-product case and a large pre-product case. For this talk, I will not have much to say about the large case. We didn't make any new progress on the large case. It's a small case that's the focus of this talk. And then it appears, at least in my looking through the literature, there isn't much written about the computational complexity of this problem. So I think that's also of interest to try to make some progress on that third problem. And so here then to try to say it, so I'm going to talk about our main result and then give some more details later. So this then is our main result is that, and the only unfortunate thing about this is there's some specific notation which I need to explain to you later. So, and our names for this is just built on notation in a proposition, which I will show you in a bit. So d delta for right now, this is meaningless. It's just saying that there are ways of generating potential completions of a given pre-product. And there are two methods which we are investigating. We call the method of Richard Pinch the CD method. That's one way of generating completions for a pre-product. And we've come up with a new way, which we call the d delta method. And then if one wants to tabulate all Carmichael numbers for all pre-products less than X, then the number of inner loop calls you have to make is then that big O expression given there. Now, this is not the usual way of measuring time complexity. Usually we would want bit operations or arithmetic operations. So if one would prefer, then you could multiply by your cost of whatever your favorite primality is. So I'll describe later what's going on inside the inner loop. The thing that dominates is primality of Q and R. And
How close to the truth is this big O estimate?
so that is a very good question. Can I answer it off the top of my head?
How close to the truth is this big O estimate?
And let me repeat it for the people on Zoom. So the question is, how close to the truth is this big O estimate? And I have to say that I don't have a good sense of what a lower bound might be. Let's see, if we somehow magically could pick out all the pairs QR. So I'm just thinking about the three, here's a partial answer to this question. In the case for Carmichael numbers with 3 prime factors, we have a soft big O of being able to tabulate them all up to b to the 2/3 as our complexity utilizing this theorem. What basically ends up happening in the 3 Carmichael case is that it's all small, is what it amounts to. And let's see, is it a conjecture or is it a theorem of Granville that there is b to the 1/3 Carmichael numbers asymptotically, b to the 1/3 with some log factors of Carmichael numbers with 3 prime factors. So I think that gives a sense of the gap here that for 3 prime factors, we're at b to the 2/3 where one would hope for, you only got to touch each Carmichael once, and that would be b to the 1/3. Right, one last note about primality. In implementing this, we went through several iterations of the code with several different primality tests and primality proofs. We thought a lot about what might be appropriate there. And where we landed on after several attempts was just to use GMP's probable prime. So there's going to be a caveat in things in the data that I report. The caveat is that when I claim I have a Carmichael number, there is a possibility that one of the Q's or the R's is actually a Bailey PSW pseudoprime, which would be exciting if that was the case. That would be fantastic. So GMP's probable prime function now uses the Bailey PSW test, and that's what I landed on. And the plan for future work is to do post-processing, to do primality proving on Q and R, just haven't implemented that yet. So that's why this theorem is expressed in this way, is that as we were developing it, we went through several different primality tests that we were doing. And here is our best attempt at coming up with a comparison to previous work. So our analysis of Richard Pinch's method requires that number of inner loop calls. And for us, it's going to be this on average. So this is a theorem depending upon the sum of a divisor function. And then if you take it on average, then you end up with that per p instead. And so this comparison, the thing to note is that we're better in a lot of cases, but not all cases, which I'll say a bit more on the next slide. So the main idea is the short version of what we've done is we've replaced a loop over an interval with a loop over divisors. This has risks, but we managed to take care of the details that come about from this. So we kept average time and space low with an incremental sieve. And Lola in her talk talked about different possible sieves that one could employ. The incremental sieve for us was convenient, mostly because it was the easiest for us to implement, that was compact so that the space savings were reasonable. And it was, the incremental part was nice in terms of stopping and starting and thinking of how we thought about the code. So one could replace an incremental sieve with another sieve here, just that's what was convenient for us. And so the advantages of the new result is that we've removed the dependence on D. Let me describe again what D is. So if we are fixing a pre-product P with D minus 2 prime factors, so the idea of D is that's the number of prime factors in the Carmichael number that you're constructing. That's what the D notation is. So in the CD method, you end up needing a number of inner loop calls that depends upon that D. If D is 3, so if you're constructing Carmichael numbers with 3 prime factors, then this just becomes a capital P, and that's great. And in fact, it's better than our method. So capital P log P versus capital P log P squared. But as soon as one's constructing Carmichael numbers with more prime factors, then using the D delta method is better, at least on average, not necessarily in every case, but at least on average. And if one looks at, I'm going to talk more about Richard's succession of constructions. Where he ended up was that this CD method was only really effective in practice for Carmichael numbers with 3 prime factors, and then as soon as getting to Carmichael numbers with 4 prime factors, using different methods in order to overcome this disadvantage. So before I get into other details, this then is sort of the key takeaway. So the key takeaway is that we're tabulating Carmichael numbers, and the advantage is that we're replacing one inner loop with a different inner loop, and that's giving us an advantage. That's the key takeaway. Are there questions before I move on to other details? Okay, so I want to give you a little bit more motivation, other reasons to care about this problem, other than the fact that Carmichael numbers are great, they're beautiful, they have nice divisibility properties. But here's a problem that has motivated people for a while, is trying to figure out, so C of X, when is it, so for sufficiently large X, it's greater than X to the beta, and what values of beta can we get? So C of X being the count of Carmichael numbers up to X. So in Alford Granville Pomerantz's proof, it was 2/7 is the value that they got. When I looked through the literature, this is the best one I found, Harmon 2005, 0.33. And then Richard in his, let's see, 2006 was the one, that wasn't, I don't think that was your last tabulation either. I just didn't find what the new number was for, I didn't do the work to figure out the new number. So at least this is not necessarily the most recent, but this is a result of Richard, is that it's greater than X to the 3/4 for 10 to the 18th. And this is a story I'm hearing secondhand, but secondhand I heard that Selfridge was challenging the community to figure out for which bound X does the count of Carmichael numbers finally get bigger than X to the 0.5, because Erdős had conjectured that it should be bigger than X to the 1 minus epsilon. And so trying to figure out when exactly is it bigger than 0.5 is an interesting question, and one that tabulating gets us further progress on. Yeah.
Sorry, the Farman theorem is, that supplies people all sufficiently large X. But the Erdős conjecture is just that there exists.
And then for, yeah, so let me see where, what's the right quantifiers here? So for every epsilon, right, so for every epsilon, you can find sufficiently large X so that it gets bigger. So at the Erdős conjecture would be at some point it's bigger than X to the 0.5, at some point it's bigger than X to the 0.7, at some point it's bigger than X to the 0.9.
Then for all X,
and then for all after that, yeah.
That's not what's written on the slide.
So this is one interesting question that one might ask about Carmichael numbers, and there's a whole variety of others, and I encourage you to look at Richard Pinch's papers. He's got statistics of all kinds. So once one has a tabulation algorithm, then one can answer a variety of questions about Carmichael numbers. So more speculative here, constructing other pseudoprimes. So from the field of studying pseudoprimes right now, I would say that the most important thing from a motivation standpoint are Bailey PSW pseudoprimes. So this talk is not about them, but I do want to give a plug because it's fun and it's interesting and it definitely matters. So a Bailey PSW test means doing a single base 2 Fermat test and then doing a single Lucas test, but you've picked your Lucas, your polynomial of definition correctly so that the discriminant is -1 so that you have an independence in some sense between the two tests. If you're not careful, the Lucas test has overlap with the base 2 Fermat test. You want to choose your discriminants so that they don't have overlap. And then from there, one can turn this into a primality test by doing a base 2 Fermat, doing the appropriate Lucas thing. If it'll either tell you it's composite or it doesn't, and then you guess it's prime. So notably, this is significantly cheaper, and this has now been, from what I can tell, in every computer algebra system. So I know for sure GMP, Paris, Mathematica, and I'm sure other ones are using this now too. It seems it's become the standard for primality testing. And notably, we have no examples of a Bailey PSW pseudoprime. We have failed tabulations. So we have lower bounds. There are no Bailey PSW pseudoprimes up to bounds. That's interesting. We have no proof that they exist, no proof that there are infinitely many, no proof that they don't exist. It's just wide open. So there's interesting problems abound. So, that's sort of where I'm always thinking about aiming in that direction. This paper is not about Bailey PSW, but you never know. What we're doing is we're tabulating Carmichael numbers. The techniques that are developed might help for constructing other pseudoprimes on a more speculative.
Yeah.
Or does this mean you ran another way to test on the Carmichael factors in the Carmichael?
So haven't yet. So that once again, that's the post-processing I want to do. That's exactly right. That's exactly right. So that's something I want to do, and I was focusing between submitting and now I was focusing on the hybrid, making the code more efficient, but I want to do post-processing like that. I just haven't done that. So the question, by the way, I should repeat the question. The question was, just throw a Miller-Rabin or other techniques at the list of Carmichael numbers to see if you get lucky. So that's exactly right. I plan to do exactly that, just haven't done it yet. And it is notable that our new method constructs much larger Carmichael numbers. So we're finding all completions for a given free product. And so we are getting much larger Carmichael numbers than would appear in a standard tabulation. And then if we're interested in a tabulation, we just throw them out. So here's an example. Here's a Carmichael number, free product 999983. This is a Carmichael number that completes that particular free product. And so one can end up with quite large Carmichael numbers. And then if you're only tabulating up to 64 or 128 bits, then you just end up throwing it out. So you never know. So we could do post-processing before we throw it out. Something. Okay, I definitely want to tell you about Richard's previous tabulations. So we've got a whole series, and this, to my knowledge, is the current state. Current record is 10 to the 21 is the current upper bound that I know of, and we haven't yet done the work to take our small pre-product and employ it for overall tabulations. But we're hopeful that we can extend this to 10 to the 24, but we haven't done it yet. So this is our tabulations that we have, and the overall method is a pre-product method. So this is now giving some notation on things I said earlier. We're going to construct Carmichael numbers in factored form. D is going to be the number of prime factors. We know that D has to be 3. Can't have Carmichael numbers with 2 prime factors, so it has to be at least 3. And then we're going to construct a pre-product, and then we're going to call the last 2 the completion primes, Q and R, and then we're trying to figure out what are candidates for Q and R, and then we're going to do tests to narrow in on them. And then we end up with these 2 cases to consider. So when P is large, you can start with a pre-product, sieve for Q, then search for R in an arithmetic progression. And when P is small, then you're finding Q and R as a pair. And those are the two general techniques. For us, we're focusing on small, so I'm not going to say any more about large. We have nothing to contribute on that case. And so this then is the key proposition. This is where our notational names come from. So I want to spend just a bit on this proposition due to the pinch. So if we've got, so what we have is we've got some pre-product P, and we're constructing this delta CD minus P squared, and then we have this holds. We've got that assuming it is a Carmichael number, Q has to have this form, R has to have this form, and the C and the D that went into it has to fall into this interval. And so the CD method then is to look at all the CD pairs that fall in that interval, and then you're going to test for divisibility, you're going to test for integrality, you're going to test for primality. So this is a necessary condition. And so let's see if I got that right. If it's so necessary condition. And so then one looks at all the CD pairs in the interval, you test, and the ones that you find become your Carmichael completions. Importantly, as a corollary, there's only finally many. So that's important. And the D delta method then is that what we're going to do instead is pick a D, pick a divisor delta, and then work through it that way. So that's our insight here, is that rather than looking at pairs CD and then checking these, we can pick a D, pick a divisor delta, and then go through and check the rest of the proposition. So that's the reordering. So in terms, I'm going to be, let's see, in terms of time, I should close up in 3 minutes or so. So let me just say, I'm going to go, I'm just going to make a couple of points, and these are, for more details, one can definitely take a look at the paper. But the idea here is when one does analysis, you're doing a double nested loop, you've got an interval length, you've got a cost for the arithmetic regression, you sum over D, you end up with this. That's where we got that result. And then in terms of new work, here's another way of saying what I said earlier. So this is just pseudocode notation for exactly the same thing, the new idea. And so what do we need? I haven't emphasized this yet. We do need a whole bunch of prime factorizations. So we're finding divisors of P minus 1, P plus D for a whole bunch of D. So we need a whole bunch of factorizations. And if one was to do this ad hoc, it could be very expensive, but with sieve techniques, one can generate factorizations for an entire interval quickly on average. And so that's the insight here, is that it's not so bad to get a bunch of factorizations and then to employ them to find these divisors. So these are the things you have to check. So you pick your D, you pick your divisor, you have to check that that's an integer, you have to check that that's prime, you have to check that that's integer and prime, you have to check that it passes the Korselt's criterion. And this is not written in the order it's implemented. In terms of implementation, you should do the prime checks last. Those are the most expensive, and that's what dominates from an asymptotic point of view. And so in terms of whether this works, so tau here is the count of divisors. So what we're really doing is we're comparing two quantities. On the one hand, the amount of work that was done per D value for the CD method is this LP over D, and instead the amount of work that we do is dependent upon the number of divisors. So one can get then a hybrid method. One can, once you've got a D value, you can compute LP over D, you can compute tau, you can compare them. Depending on which is bigger, you can either do the CD method or do the D delta method. And let me then jump ahead to the timings. I think it's appropriate. So this is some more analysis. One more example. So here's an example of this. We've got a pre-product. So third number, that's the smallest Carmichael number with exactly 6 prime factors. Generating these 4 numbers, it does require checking a lot of things. So about 9 million D delta pairs or about 2.8 billion CD pairs in order to track down these 4 numbers. So there, to Andrew's question from before, I bet there's still improvements that could be made to this, because it really feels like there's still a lot of wasted work. You're just searching around for candidates, and then you're doing these tests to exclude them. And we've managed to reduce the number of candidates searched, but it's still a million pairs just to find 4 Carmichael numbers. Feels like there's a lot of ways to go. So further improvements definitely could be possible. And okay, so then I am going to skip over this to jump to the timings and finish with that. And so I've got 2 different timings tables here. One is for all pre-products and one is for prime pre-products. And the reason for this is that prime pre-products, that's the case where the CD method does the best. So what to get out of this table is that if we're looking at all pre-products, then the D delta method does better than the CD method. But if we do a hybrid method where we combine the 2, then it does better than both. And similarly, if we restrict to prime pre-products, then the CD method does better than the D delta method in this case, but a hybrid method of the 2 does better than both. And so there's the conclusion is that there's a speed up in the case where we have a fixed pre-product, and more generally, if we have all pre-products over a range, there's a speed up. And so what this means then in terms of tabulation. So currently what we have is 10 to the 7th. We want to complete, we've got tabulation for all pre-products up to 10 to the 7th. We want to get up to 10 to the 8th. That's ongoing work. And we want to complete a Carmichael tabulation up to 10 to the 24. So my last thought on this is just that if we can improve, we don't have any improvements to the large pre-product case, but with improvements to the small pre-product case, we can push out further the small case. We can go further faster, and so we can do less work then on the large case. That at least is what we're hoping, but that's still future work to find out. So thanks for your attention, everybody. Thank you.